Have you ever thought about, like how some people are just like good at things? You know what I mean? Like
Yeah.
music or math, stuff like that. It's like they were just born with it.
Right, like a natural talent.
Exactly. So what if we could do that with AI? Like give AI that same kind of edge?
That's a really interesting thought.
Well, that's actually what we're diving into today. It all has to do with this thing called inductive bias, and it's all about like how it shapes what neural networks can learn.
Oh, cool.
Yeah. So we're going to unpack some research today, and it's exploring whether you can make different neural networks all learn the same way, even if they're built differently,
Mm.
which is kind of wild when you think about it.
Yeah, I mean, it really comes down to how these networks are set up, like initially, like their learning style in a way.
Uh-huh.
So some networks are made for like visual stuff,
Mm-hmm.
others for language, you know, and some for like more abstract reasoning.
Right.
The big question is, can we like mess with this initial setup to make them all into like super learners?
It's almost like giving them like good study habits right from the start.
Yeah, exactly. Instead of just like throwing a bunch of data at them and just like hoping for the best.
Hoping they figure it out.
Yeah. So the researchers, they tested this idea using some pretty clever tasks. Like they had the networks learn concepts from just images.
Interesting.
They even had them solve modular arithmetic problems,
Yeah.
math,
Oh, wow.
and even like quickly learn to recognize handwritten characters, like all sorts of things.
That's awesome. So to do this, they experimented with 4 like major types of neural networks.
Okay.
And you can think of these like as different kinds of brains,
Okay.
each one with its own like strengths and weaknesses.
Mm-hmm.
So first we've got the vanilla network. It's called the MLP.
MLP. Got it.
And this one's like your general purpose learner. It's like a good starting point, I guess,
Mm-hmm.
but it doesn't really have any special assumptions about the data. It's just like, here you go, learn this.
Okay, so it's like that student that shows up to class with like no preconceived notions, just ready to learn.
Exactly.
Okay, cool. What about the other brains?
So then you have the CNN, and this one's like the visual whiz.
Uh-huh.
This one is built for images, and it processes information, kind of like our own visual systems.
Mm-hmm.
It focuses on nearby features to try to figure out like what it's looking at. So it's really good at like picking out patterns and details in visual data.
So if the MLP is like the generalist student, the CNN is like the art student. Like they can spot every little detail in a painting.
Exactly. Like a detective,
Yeah.
scanning the scene for clues.
Okay, so we got the generalist, we got the art student detective. What about the other two types?
Okay, so now let's talk about the LSTM.
LSTM.
And this one is like the storyteller.
Ooh.
This one is the master of sequences.
Mm.
So it remembers patterns over time, just like you would when you're like following a story or listening to a song.
Okay.
It's kind of like the reason your phone can predict the next word you type.
Yeah.
It's learned the patterns of language.
It's really freaky when it does that.
Right.
Okay, so the CNN is the detective. The MLP is the all-arounder. The LSTM is the historian.
Yeah.
Putting it all together. Context.
You got it.
And that leaves one last one.
Right.
What was it called again? The transformer.
The transformer. You got it.
Okay, remind me what that one is.
So this one's like the conductor of an orchestra.
Okay.
It can focus on any part of the input, no matter how far apart. So it's really good at things that require understanding the relationships between like distant pieces of information.
Okay, I'm with you.
So think about like reading a complex article, and the meaning of a sentence depends on something you read like paragraphs ago.
Oh, yeah.
The transformer can make those connections, like pulling all the different parts together.
Okay, so if the LSTM is the historian, piecing together the narrative, the transformer is like the philosopher seeing the big picture.
Exactly. You got it.
Okay, this is all pretty fascinating stuff, but how does it relate to like the research we're talking about today?
So usually when these networks like start learning, their connections are totally random. Think of it like starting with a jumbled puzzle. And as you might guess, some brains are better for certain tasks than others.
Well, yeah, I mean, you wouldn't ask a fish to climb a tree.
Right. Exactly. Each network has its own strengths.
Okay.
And that's exactly what they found in their experiments, like the first round. But what they really wanted to know was, could they, like even the playing field, could they somehow make all these different brains like super learners, regardless of their strengths and weaknesses?
That's where the idea of meta-learning comes in, right?
Yeah.
It's like giving all the students the same set of tools, no matter what their natural ability is, like to help them excel in any subject.
Exactly.
So tell me more about how this works.
So meta-learning is, it's basically all about teaching networks how to learn.
Okay.
Like not changing their structure or anything,
Mm-hmm.
but more like fine-tuning that initial setup,
Okay.
based on a bunch of practice problems.
So it's like they're practicing how to learn.
Exactly. It's like imagine you're getting ready for some huge exam.
Right.
Instead of cramming the night before, you come up with like a really solid study plan.
Right.
You figure out how to memorize things better, and you practice different kinds of questions.
Yeah.
That's kind of what meta learning is doing for these networks.
Aha. So it's like giving them a head start.
Yeah, it's giving them like effective learning strategies right from the beginning.
So instead of just being good at one thing, they're becoming better learners overall.
Exactly.
Like more adaptable.
Right, they can take on more challenges.
That's pretty awesome.
Yeah, and the researchers put this to the test with those tasks we were talking about earlier.
Right.
Like first they did that concept learning thing.
Yeah.
So basically training the networks to recognize abstract concepts from images.
Okay.
So like think about looking at a bunch of photos of different fruits and you have to learn to tell the difference between like apples and oranges
Yeah.
based on their shape and color and all that.
Okay, so they're teaching these networks to be fruit experts.
Right, exactly.
Okay, so what happened? Did the CNN, like the visual one, did that one just like naturally do the best?
Yeah, so when they trained them the usual way, starting with those random connections,
Right.
the CNN did do the best.
Oh, yeah.
It's built for visual stuff, so that makes sense.
Of course.
But here's the really cool part. When they did the meta-learning thing, the difference between the networks basically disappeared.
Wait, so you're saying the storyteller and the philosopher could pick out apples and oranges just as well as the visual whiz?
Oh. Pretty much.
Wow.
Because of that meta-learning training.
They were all equally good at being fruit experts.
Yeah, they had the tools to succeed no matter what they were good at the beginning.
It's like everyone gets a superpower.
Yeah, exactly. It's like finding that one study technique that works for every subject.
That would be amazing.
Right. It kind of challenges that whole idea of being good at certain things or not.
Like being a math person.
Yeah. Maybe if we learn the right way, we can all learn anything.
That's a huge idea.
It is, but we got to remember meta-learning isn't a magic solution.
Right.
There are still limits to what it can do.
Okay.
So to test that, they threw in something totally different, a task that needed a different kind of thinking. Modular arithmetic.
Okay, so math is not my thing. Can you break that down for me?
Yeah, so modular arithmetic is all about remainders.
Okay.
Like you divide a number and you see what's left over.
Okay.
Like if you divide 12 by 5, you get a remainder of 2.
Okay, I get it.
It's used in stuff like cryptography and computer science, and it takes a different way of thinking.
So it's like you're asking a painter to suddenly switch from landscapes to abstract art.
Right, exactly.
Like they have the skills, but they need a whole new approach.
Yeah, and that's what happened. Even the networks that had that meta training, they struggled with this modular arithmetic stuff.
So even with the best study habits, you're going to hit a wall if it's something you've never seen before.
Exactly. Meta learning might make you a faster learner, but doesn't mean, everything.
It's like you can lead a horse to water, but you can't make it drink.
Uh-huh. That's a good one.
Even with the right tools, there's a limit to how much you can learn.
Yeah, for sure. And this brings up some really interesting questions about learning itself, like for both machines and humans.
Okay, now we're getting into it. We're going beyond the technical stuff and talking about like intelligence and the limits of learning.
Right, it's big picture stuff.
Okay, I'm ready. Let's go deeper. What are like the key takeaways here? And how does all this affect how we think about AI and ourselves? So we've seen that meta-learning can help networks learn better, but it's not like a magic fix.
Right.
There are still limits, like how much they can handle new stuff. So what does this all mean for AI? Like, are we about to have machines thinking for themselves, or is that just like a sci-fi dream?
Well, that's the big question, isn't it? I mean, this research is really cool because it makes us rethink what AI can actually do.
Yeah.
Like if we can change how a network starts off and teach it how to learn, who knows what it could do? We might see it solving problems in ways we never thought of. We might even see something like artificial intuition.
Hold on, artificial intuition? That sounds kind of crazy. We're talking about machines here, not like some mystical beings. How could a network have intuition?
Well, think about it. Intuition is like knowing something without knowing how you know it.
Yeah.
Like a feeling, right?
All right.
So picture a network that's learned from tons of data, seen all kinds of patterns.
Okay.
It might start to make connections that go beyond what we programmed.
Okay. I'm kind of following you.
It's not magic. It's just a different way of thinking.
So it's like it's understanding the world in a deeper way, not just following rules.
Exactly. But that brings up another issue.
Oh, yeah.
What if these AI start making decisions that we don't get?
Right.
How do we make sure they're still doing what we want them to do?
That's a good point.
Yeah, researchers are working on that right now. Like, what are the ethics of all this? As AI gets smarter, we have to make sure it's safe and actually helps people.
It's like walking a tightrope, right? On one side, we could have AI solving huge problems, but on the other side, it could be dangerous if we're not careful.
Yeah, exactly. It's a tough balance, but we have to get it right. You know, this research on inductive bias and meta learning, it gives us a peek into the future.
Okay.
A future where AI isn't just a tool, but like a partner working with us to figure things out.
Wow. So it's not just about AI getting smarter, it's about us getting smarter too.
That's a good way to put it.
Well, we've come to the end of our deep dive. We've talked about a lot, like how important those initial conditions are, the potential of meta-learning, and what this all means for AI and for us. It's been a lot to take in, and I hope you'll keep thinking about it all. Thanks for listening, and until next time, keep learning, keep asking those big questions.